In this presentation, we are going to look at spanning trees. So let's look at the question here now. A graph of 5 vertices, A, B, C, D, and E, has the following adjacency list. What we're asked to do is draw out this graph, G. So this is actually a tree. It's a general type of graph. So what I'm going to do first off is just draw out the graph here. So we have vertex A, and that's connected to B, which I'm going to draw over here, and E, which I'm going to draw down here. So let's write that in, A, B, and E. Just as a quick remark, actually, usually if you're drawing a graph, they can be quite... basically, the second attempt is usually a bit more easier to look at. This is my actually second attempt at doing this. So I'm going to draw vertex D here and C over here on the right. So that's A and B. B is connected to A, C, and D. So I'm going to draw D down here, and I'm going to draw C over here. C, and just draw that in properly. That's D down there. Next one is C is connected to B and D, so just connect that up there. And finally, D is connected to B, C, and E. So we just have to connect it to E over there. And finally, E is connected to D and A. So that's the graph done. So again, that is a second attempt. Usually it takes 1 or 2 attempts to come up with a nice simple looking graph. So what we're going to do now is go on to the next question here. Draw a spanning tree of G. So what I'm going to do here is actually just draw a spanning tree of G. I'm going to do a simple, I had A down here, E down here at the bottom. I had A here, B here, C here, D down here. Simple spanning tree would be, let's say, a path graph, essentially just going from one vertex to the next until we've visited them all. And in that diagram, no vertex has degree greater than 2. So that's a spanning tree of G. Okay. Now, just a few remarks there. How many edges are there? There are 4 edges. And this is not actually part of the question, but it really actually helps us understand it. And what I'm going to do here also is I'm just going to put in the degree and the degree sequence. So 1, 2, 2, and 1. So the degree sequence here is 2, 2, 2, 1, and 1. And by the way, the sum of the degree sequence is 8. Okay. That's just going to help us later on, actually. So that's why I mention it now. So draw all the non-isomorphic spanning trees of G and call this set S. So let's just consider a few remarks first off. That just scroll back here. What I'm going to do is basically state that all non-isomorphic spanning trees of G and call this set S. So a quick, all non-isomorphic spanning trees will have the following characteristic. There'll be 4 edges. The sum of the degree sequence is going to be 8. It has to be connected. Okay, a spanning tree has to be a connected graph. And also, just look over here. Let's write out the degree sequence of the vertices of G, the actual degree, the underlying graph itself. 2, 3, 2, 3, 2. So in this case, the highest possible vertex, the highest possible degree of any vertex is 3. That would be also applicable to any spanning tree. So the highest vertex, the highest degree of any vertex is 3. And also there's going to be 5 elements in the degree sequence. So draw out all the non-isomorphic spanning trees of G and call this set S. So I'm just going to scroll back here for a second and just talk about this here for again. This is what we call a path graph. Okay, this type of graph here. And path graphs are always isomorphic to each other. So I'm just going to draw a different possible path graph through G. Let's start down here. A, E, B, C, and then down to D. I'll just put in the vertices again here. E, A, B, C, and D. Now that's a spanning tree of G, and it's a path graph, but it's actually isomorphic to what we've just drawn already. And in fact, any possible path graph that is a spanning graph, the spanning tree of G, is going to be isomorphic. And again, no matter which way we draw a path graph, the degree sequence is going to be that. Okay, so draw a spanning tree of G. We've chosen a path graph there. Essentially, draw all the non-isomorphic spanning trees of G and call this set S. Essentially, what we're going to do is come up with a different type of spanning tree that is not a path graph. Okay, so let's just look at that now again. I'll just put in our vertices here. So what I'm going to do in this case is I'm going to have in our tree, a spanning tree, a node, a vertex that has degree 3. Okay. And so this is an alternative spanning graph that is not isomorphic to what I've done already. So degree sequence down here is 1, 2, 3, 1, and 1. Actually, let's just write in the proper names of the vertices. E, A, B, C, and D. Okay. Now, the degree sequence for that graph is 3, 2, 1, 1, 1. And that does actually add up to 8 also. So we've come up with 2 non-isomorphic spanning trees, but can we come up with a third one? Now just remember our constraints. We only have 4 edges. There are 5 vertices, 4 edges, and the sum of the degree sequence is 8. And also, the highest degree value is 3. We can't have a vertex of degree 4. So what's another way of coming up with a path graph here, or spanning tree of this? So we could try and use something. We could try and sort of have base our answer on D. So let's just try out this here for a second. So A, D, B. This is a possible answer. A, E, B, D, and C. Now you might notice here we have this is a different possible answer. This is a different spanning tree. But is it isomorphic or non-isomorphic to something I've already suggested? So we have 1, 2, 1, 1, and 3 here. So we have pretty much the same degree sequence. In fact, this is isomorphic to what we have already. So it's isomorphic to previous answer. Okay, so can we come up with another way of coming up with another possible answer that's not isomorphic to what we've done already? Well, we actually can't. If you just consider the constraints where we have listed out already, that for the summation to be 8, which is required, the vertex of degree 3 must be connected to the vertex of degree 2. Because it doesn't make sense otherwise. It won't be connected if you do it any other way. Or it might not even make sense any other way. So no matter what you do, the vertex of degree 3 is always going to be connected to the vertex of degree 2. And so essentially, no matter which way you do it, they're always going to be isomorphic to each other. So the two answers I've come up with already, the path graph and the previous, that one there, these are the only two possible isomorphic spanning trees of G. Okay, it's not possible to come up with any other ones due to the constraints. So let's draw all the non-isomorphic spanning graphs of G and call it set S. Okay, so that is the end of our presentation.